Leeds International School, Form 7, Mathematics, Pure Mathematics 4, Chapter 1, Proof. Learning Objectives. After completing this chapter, you should be able to use proof by contradiction to prove true statements. Prior knowledge check. Factorize. X squared minus 6x plus 5. Quadratic expression. So you need to learn how to factorize quadratic expression. X squared minus 16, so you can write it as x squared minus 4 squared. Right? So difference of 2 squared. So 9x squared minus 25. So you can write it as 3x squared minus 5 squared. Pure Mathematics 1. And IGCSE Mathematics. So you need to revise. Proof by contradiction. A contradiction is a disagreement between two statements, which means that both cannot be true. So proof by contradiction is powerful technique. To prove a statement by contradiction, you start by assuming it is not true. You then use logical steps to show that this assumption leads to something impossible. Either a contradiction of assumption or contradiction of fact you know to be true. You can conclude that your assumption was incorrect and the original statement was true. So we'll learn this by using examples. Example number 1. Prove by contradiction that there is no greatest odd integer. So we have to prove by contradiction there is no greatest odd integer. So we will assume the opposite of this. The opposite of this statement, assumption. So there is a greatest odd integer n. So then n plus 2. So we can get next odd number by adding 2 to that integer is also an integer. So then we can write it as n plus 2 greater than n. So you can see this n, odd, 2, number 2, even, odd plus even is equal to odd number. So you need to use logical steps. You need to use logical steps to reach a contradiction. So you need to show your working clearly. So there exists an odd integer greater than n. So there exists an odd integer n plus 2 greater than n. This contradicts the assumption. So that greatest odd integer is n. Therefore, there is no greatest odd integer. So you need to finish your proof by concluding the original statement must be true. Example number 2. Prove by contradiction that if n squared is even, then n must be even. So we have to prove by contradiction that if n squared is even, then n must be even. So we will assume the opposite of this. The opposite of this statement, we can write like this, assumption. So there exists a number n such that n squared is even but n is odd. Opposite of this statement. So here our assumption, the opposite of this. So then n is odd. So we can write any odd number like 2k plus 1. Can write any odd number in the form 2k plus 1. So where k is an integer. So integer multiplied by 2, you will get even number. So even number plus 1, you will get odd number. So then we'll take n squared. So we need to square both sides. 2k plus 1 square. So a plus b square. So first term square, 2 times first term second term, and last term square. So we'll get 4k squared plus 4k plus 1. So now we can take 2 common factor. 2 as a common factor, take 2 out from the bracket. So then it will give 2k squared plus 2k, cross bracket plus 1. So again, so all multiples of 2, even number. So even number plus 1 is an odd number. So 1 more than multiples of 2 is an odd number. Right? So k is an integer. So then 2k squared plus 2k is also an integer. So integer multiplied by 2, you will get even number. So even number plus 1, again you will get odd number. So this side odd, so we can take n squared is odd. So this contradicts the assumption. So this contradicts the assumption n squared is even. So therefore, if n squared is even, n must be even. So n squared is even, n must be even. So you need to finish your proof by concluding that the original statement must be. So this is the original statement must be because of this contradiction. Rational number. The rational number can be written as a divided by b. So numerator a, the denominator b. So where a and b are integers. So definitions of the rational number. So we can write the definition of rational number like this. A divided by b, where a and b are integers, elements of integer. So notation, the rational number, letter like q. So then the opposite of rational, so we call it as irrational number. So irrational number cannot be expressed in the form a divided by b. So where a and b are integers. So you need this knowledge to solve the next problem. So example number 3. Prove by contradiction that root 2 is an rational number. So we have to prove by contradiction that root 2 is an irrational number. So we will assume the opposite of this. The opposite of this statement, root 2 is a rational number. Assumption. So therefore our assumption, root 2 is a rational number. So then we can write root 2 as a divided by b. So a comma b, element of z, integer. So this is the definition. So this is the definition of rational numbers. So you can't change the definitions in mathematics. So also assume that this fraction, so this fraction, numerator and denominator, cannot be reduced further. Cannot be reduced further. So there are no common factors between a and b. So you can't get equivalent fractions by dividing numerator and denominator by the same number. So this fraction cannot be reduced further. So if a and b, so they have a common factor, so you could just cancel out and can get equivalent fraction in its simplest form. So cannot reduce. So there are no common factors between a and b. So square it, both sides. So 2 square it is 2, a square divided by b square. So we can rearrange like this, make a subject and multiply b into this side. You will get a squared equal to b square. So square both sides. So make a square the subject. So you can see this 2 times another number. So that means even. So this means a squared must be even. So a squared must be even. So a is also even. So we did that earlier here. So n squared is even, then n must be even. N squared is even, so then n must be even. So we can use that here. So a squared must be even, so n is also even, right? So then a is even. So even number. So then it can be expressed in the form 2n. So if it is even number, you can write 2 times integer. 2 times integer. So we can replace this a by 2n. So a squared means 2n square. Right? So 2n square means 4n squared. Right? So then it equal to so 4n squared, it's equal to, divide both sides by 2, you will get 2n squared equal b squared. So what's the meaning of this? So this means that b squared must be even. So because 2 times integer square. So then b squared must be even. So b is also even. So by using previous example. So if a and b both even, so if a and b are both even, so we can find the common factor 2. No? So even number you can write 2 times integer. Right? So we can find the common factor 2. So we can cancel out. So this contradicts this statement. So also assume this fraction cannot be reduced further. So there are no common factors between a and b. So this contradicts the statement a and b have no common factors. Therefore, so root 2 is an irrational number. So you need to finish your proof by concluding that the original statement must be true. So example number 4. So prove by contradiction that, so we have to prove by contradiction so that there are infinite many prime numbers So definitely many prime numbers. So what is the opposite of this statement? So we will assume the opposite of this. So the opposite of this statement, so we can write there is a finite number of prime numbers. There is a finite number of prime numbers. Assumption. So let us, we can list all the prime numbers. Take P1, P2, P3 up to Pn. So list all the prime numbers. So there are finite number of prime numbers. So you can write like this up to n. So list all possible prime numbers. So consider the numbers. So we can take the new number capital N. So is 1 more than the product of the existing prime numbers. So you can multiply all prime numbers and add 1 more than. So new number, so you can take it as n. So when you divide capital N, so by any prime number, P1, P2, P3 up to Pn, so you get a remainder of 1. So for none of the prime numbers up to P1, P2, P3 up to Pn is a factor of n. So why? Remainder equals to 1. So take this one. So if you divide by P1, so you will get the remaining part as a quotient and this one as a remainder. So n must either be prime or have a prime factor, so which is not in this list. So all possible prime factors. So this is contradiction. So therefore, there is an infinitely many prime numbers. So we need to prove like this, step by step you need to prove. So exercise 1a. So you need to do this as homework. So we'll discuss each and every question inside the class. Summary of key points. So thank you for watching.